Hello everyone, welcome back to my channel Shraddha's Physics. This video is based on statistical mechanics for the core 14. Today we will see the unit 4 of Kirchhoff's law. So the Kirchhoff's law states that the ratio of the emissive power to the absorptive power for a given wavelength at a given temperature, it is the same for all the bodies and it is equal to the emissive power of a perfectly black body at that temperature. So, we have already discussed what is emissive power. Emissive power means the spectral emissive power of a body at a particular wavelength. It is the radiant energy emitted per unit time per unit surface area of the body within a unit wavelength range, that is known as your emissive power. And the absorptive power, it is the absorptive power of a body at a particular temperature and for a particular wavelength. It is the ratio of the radiant energy absorbed per unit surface area per unit time to the total energy incident on the same area of the body in unit time within a unit wavelength range. So, here we will see what is Kirchhoff's law. Now, suppose A lambda, it is the absorptive power of a body and dq be the quantity of heat energy it lying within the wavelength lambda and lambda plus d lambda, it incident on the unit area of the surface in 1 second. Suppose then the quantity of heat energy absorbed by the surface, it will be given by A lambda dq. So, the remaining energy will be the total heat, that is dq, minus the absorptive power, that is A lambda into the dq, that will be dq minus A lambda dq equal to dq, taking dq common, this will be dq whole into 1 minus A lambda. This will be either reflected or transmitted or both. Okay. It means that after absorption, this remaining, it may be get reflected or transmitted or both. If E lambda, it is the emissive power, then the amount of energy emitted per second per unit area between the wavelength lambda and lambda plus d lambda by the virtue of the temperature, that will be E lambda d lambda. This is the emissive power in your this wavelength d lambda. So, the total energy given out per second per unit area of the surface will be, this is 1 minus A lambda into dq, the remaining part, that is either reflected or transmitted, plus this E lambda d lambda because of the emission. So, in case of equilibrium state, when the equilibrium state, so the total heat, that is dq, will be equal to this 1 minus A lambda dq plus E lambda. So, that is the total energy given out per second per unit area of the surface, that will be equal to the total heat. So, by solving this, so here dq, 1 into dq, that will be dq. So, dq get cancelled, this will be minus A lambda dq plus E lambda d lambda equal to 0, that is A lambda dq will be equal to E lambda d lambda. So, for a perfectly black body, A lambda equal to 1 and this E lambda equal to the capital E lambda, that this capital E lambda, this is for the perfect black body. Perfect black body emissive power is the capital E lambda. Here you can see that this dq, A lambda dq equal to E lambda d lambda. So, in place of A lambda, if I will put 1, so this will be dq. So, this dq will be equal to, in place of small E lambda, I will put capital E lambda into this is your d lambda. So, dq will be equal to E lambda into d lambda. Putting this equation, that is equation 2 in equation 1. So, in place of dq equal to E lambda d lambda. So, in place of dq, if I will put this E lambda into d lambda, this will be A lambda, E lambda into d lambda will be equal to, this is E lambda into d lambda, capital E lambda into d lambda. Okay. So, cancelling this d lambda, this will be E lambda will be equal to, capital E lambda will be equal to small e lambda divided by A lambda. So, this is known as the Kirchhoff's law. So, this Kirchhoff's law, what is Kirchhoff's law? This is the ratio of the emissive power, this is the emissive power to the absorptive power, this is the emissive power to the absorptive power for a given wavelength at a given temperature, it is the same for all the bodies, and it will be the equal to the emissive power of the black body at that temperature. This is the emissive power of the black body at that temperature. Okay. Now we will see the applications of Kirchhoff's law. This Kirchhoff's law tells that the good observers are the good emitters. It means that if a body absorbs radiations of a particular wavelength strongly, it also emits the same radiation strongly. The first application is when a polished metal ball having a black spot on its surface, it is heated to a high temperature. The black spot appears more brightly than the polished surface. So if we will take a polished metal ball and it has a black spot on its surface, it is heated to a high temperature, then this black spot it appears more brightly than the polished surface. Why? Because this black spot, which absorbs the radiation more strongly than the polished surface at the ordinary temperature, it will emit more strongly at the high temperature. Clear? So that's why this black spot appears more bright. Similarly, a piece of red glass which absorbs green light strongly, it glows with a green light when heated. So this implies that the good observers are the good emitters. The second application is when the sodium vapor is heated to a temperature high enough to emit visible radiation. Its emission spectrum consists of two yellow lines. Okay. On the other hand, when the white light is passed through a cooler sodium vapor and then seen through a spectroscope, the continuous spectrum of the white light, it is found to consist of the two dark lines in exactly the same position as the yellow lines in the emission spectrum. So, the sodium vapor which emits two yellow lines strongly is also a good absorber of light of these two wavelengths. The next application is, this Kirchhoff's law explains the origin of the Fraunhofer dark lines in sun spectrum. That is, the sun consists of a central glowing mass which gives the continuous spectrum, and it is surrounded by a color atmosphere which contains the various elements like hydrogen, nitrogen, sodium, cesium, copper, etc. in the gaseous state. When this radiation from the central mass it passes through the surrounding atmosphere, the various elements absorb these wavelengths which they can emit at a higher temperature. So it means that those wavelengths are missing from the sun spectrum and we see the dark lines in their places. And the next application is, the Kirchhoff's law is responsible for the development of the science of spectrum analysis. Here it establishes that the atoms of each element give a spectrum which is the characteristic of that element alone. So, if the characteristic spectral lines of an element are seen in a spectrum, it is certain that the element is present in the substance of which the spectrum is being taken. So, these are the applications of Kirchhoff's law. So, this is all for today. Thank you.